This video covers the second part and last part of 12.2, in which we are working with transforming data. We've talked about the power model, and now we'll sort of introduce the exponential model of curved data, and we'll sort of compare the two and figure out, like, what do we need to do to figure out which type of model is most appropriate. All right, this happens to be our last lesson of the year. That's it. Chapter 12 is it. So we're finishing up chapter 12, and this is the last part of the last lesson. All right, so this deals with data that falls into an exponential model. And so to demonstrate what an example of exponential data would look like is, let's suppose that your parents agree to pay you 1 cent today for your allowance, and then they're going to double that amount each week. So, you can see that, at first you're not making much money, right? So we'll call this week 0. You get 1 cent. Next week, week 1, you'll get 2, 4, 8. So the amount that you're getting is pretty small, but pretty quickly it jumps up. So if we were to graph this data, it would look something like this. And you can see that at the beginning, it looks as though you're getting almost nothing, right? It looks like 0, 0, 0, because we want a rather large scale on this in order to be able to fit as many weeks as possible. So you can see that this let me get rid of these, that this data is flat, it's flat, it's flat, and then all of a sudden it just jumps up. And we wouldn't even be able to fit anything more than like 13 weeks on this one graph. We would have to use a much bigger scale in order to be able to fit more on there. But the bad thing about this graph is that it doesn't really show any details for the first, I don't know, 7 or 8 weeks. It kind of looks flat, looks like it's almost got nothing, that you're getting paid almost nothing. So one way that we have of interacting with this exponential data is to plot it on a different type of graph paper. So the graph paper on the left is your typical graph paper, but this is a different type of graph paper that you may never have seen before. The x-axis is a sort of a regular scale, what they call a rectangular scale. But the vertical axis, the y-axis, is something called a logarithmic scale. So you can see here that this is a penny, right? 1 cent. And then you can see 2 cents, 3 cents, 4 cents, all the way up to 10 cents. But then the next jumps up to, from 10 cents, 20, 30, 40, 50, 60, $1, and then $2, $3, $4. So every sort of grouping of lines ends up, the lines get closer together, but every grouping of lines is another factor of 10. So if we were to graph this data, it would look something more like this. So it doesn't really help us. We can still only fit like 13 weeks on here, but you can see the detail in the lower end of this. And so what's interesting, though, is that the exponential data that we see over here, when plotted on a normal rectangular for the x, but a logarithmic scale on the y, ends up straightening out the data. And this is sort of the clue to what we're going to do here in statistics to straighten out exponential data. Okay, so instead of plotting week on x and allowance on the y, but using a logarithmic scale, instead, let's plot the week on the x-axis and log of the allowance on the y, and then just use a normal rectangular scale, and we don't have to worry about what we call semi-log paper. Semi-log because on one side it's not logarithmic, but the other side it is. So it's partially, the graph paper is partially logarithmic. So we call it semi-log paper. So in here, we just do x against the log of y, and you can see it's the same. It has the same real effect. But we don't have logarithmic graphing paper. And so instead, we're going to plot, we'll end up plotting the week against the log of the allowance or the log of the Y data. And you can see now this is fairly linear. All right, so sometimes when we are thinking about a relationship between x and y, the y value is found by repeatedly multiplying by the same constant factor. And so that is what sort of exponential is. So we take, in this case, if we look at the equation here, b is being raised to various powers, right? So if x is 1, then it's just b. If x is 2, then it's b times b, right? So you're repeatedly multiplying by b in this case. All right, so let's look at how we can transform this exponential model or exponential equation using logarithms. So if we take the log of both sides, you can see we have log y is equal to log a b to the x. So a, again, is a constant, b is a constant, x is a variable. And so using our rules for logarithms, we can break the right-hand side up. It's the log, right now it's the log of a product, a times b to the x, and so we can break that up. And so we have log a plus log b to the x. And so this x right now is an exponent, and we can take that exponent down in front using the power properties of logarithms. So we can bring that x down in front, and now we have log b, and b is a constant, so log b is a constant. So we'll just kind of write that as capital B. And then log A is a constant, so log A is a constant, so that's also sort of a constant. So you can see that this equation definitely has a linear form. X and log Y are form a linear equation. Okay, and so basically what it's saying is that for our purposes, that if the variables grow exponentially, then its logarithm will grow linearly. So we can look at a certain value of x, its output is exponential. The y value is exponential. Okay, so we're looking at an example using exponential growth. Gordon Moore is one of the founders of the Intel Corporation, and he predicted in 1965 that the number of transistors on integrated circuit chips, this is measures of processing power for computers. And so his law predicted that those number of chips would double every 18 months. And so, I'm sorry, not the number of chips, but the number of transistors on chips would double every 18 months. And so this data shows the number of transistors on each chip and the date in which that processor that had those transistors was manufactured. And you can see they grow quite substantially over the years. And so our data, our X, our date, is going to be years since 1970. And then our other data is just going to be the number of transistors. So if we plot this on, X, and for us, X is the number of years since 1970, against the number of transistors, just like we saw in the allowance problem, at the very beginning, there's almost no movement at all. In these first several decades, it really looks like we have a very flat growth. The scale that we use in order to accommodate the more recent number of transistors is so large that those first several decades look like they're pretty much flat. So this is clearly not linear data. It's curved data, exponential data, fits just the model like we were looking at with the allowance. However, if we take that data and we plot year, the normal x-axis, the year since 1970, against the natural log of the number of transistors, now the data is much more linear. Okay. And so it's reasonable to expect that we had an exponential model because x plotted against log y is no longer curved. It's fairly linear. I mean, there's still a little bit of a curve in it, right? It's not perfectly linear, but it's certainly more linear than the original exponential data. All right, so if an exponential model describes the relationship between two variables, x and y, then we expect the scatter plot of x and natural log of y to be roughly linear. And then this scatter plot of natural log of transistors versus the years since 1970 has a fairly linear pattern, especially around the year 2000. So an exponential model seems pretty good here. All right, so now we've taken Minitab and we've gotten it to give us an output from a linear regression analysis on the transformed data. So that's years since 1970 plotted against the natural log of the number of transistors. All right, so write the equation of the least squares regression line for this transformed data. All right, I'll go to it, pause the video and write that out. All right, so we know we can take the A value or the y-intercept from this spot here in our printout, and the one below it here is our slope. Okay, so that's where we got those two values. Remember that the y, the predicted y value, is not predicted number of transistors, but the predicted number of transistors, the natural log of the number of transistors. So it's natural log of that. All right, so now that we have a model, use it to predict the number of transistors on an Intel computer chip in 2020. All right, because 2020 is 50 years since 1970, we're going to put 50 in for our X, or for years since 1970. And, it's going to be obvious that that's not the final answer because that's 25, right? I mean, we've had a lot more than 25 chips on a transistor, on a chip, number of transistors on a chip much bigger than 25, but that's equal to the natural log of the number of transistors. So we need to take the the natural log of the transistors equals 25.3562. So we need to raise e to that power. Remember that natural log is log base e. And so if we take e and raise it to that power, that gives us 1.028 times 10 to the 11. So that's really big. That's about 100 billion transistors is what we would predict. All right, and then the last thing we want to look at here, similar to what we did in the last chapter, is we want to look at the residual plot. And so there does appear to be a sort of a pattern here. It's high, it's kind of back down, it's high, it's back down, it's high again. But relatively speaking, this is a much better pattern than what we would have seen if we had tried to apply a linear model to the original untransformed exponential data. Okay. Um, so discuss what this graph tells you about the appropriateness of the model. So that's kind of what we said. Um, you know, yes, there's a pattern here, but the residuals are pretty small, and this pattern is not as distinct as it would have been if we had used the original untransformed data. Okay, so the residual plot shows a distinct pattern with the residuals going from positive to negative to positive as we move from left to right. So the residuals, but the residuals are small in size relative to the transformed y values. Also, the scatter plot of the transformed data is much more linear than the original scatter plot, where we were looking at the original exponential data before we transformed it. So we're going to feel pretty comfortable using this model. All right, so basically, what are we taking away from this? So we have some curved data. All right, so is that curved data exponential or is it power? So there's two ways to check it, and this is what you have to basically take away from this last part of the section. All right, so we can either plot x against log y. We check that, see if that's linear, or we plot log x against log y, and we see which one of these is more linear. And so clearly, x against log y is linear, where log x against log y is not. So the model is clearly an exponential model, okay? So we can see that x plotted against log y is linear, and so that tells us that we have an exponential model. All right, and so another example, we have curved data again. Again, we're going to do the same thing. We're going to plot x against log y and log x against log y, and we're going to see which one of these is linear. So this time, log x against log y seems to be linear, whereas x against log y is not. So this tells us that we have a power model this time. And so we see that log x and log y, that transformed data, has a linear model. So therefore, the original data is a power model. All right, so this is your homework due next class.